My name is B. Ravindar, Assistant Professor in the Department of Electrical Electronic Engineering, BVRIT Narsapur. Today I am going to discuss on the course Power System 2 in the topic is sequence networks. So last class we discussed about on sequence component like this symmetrical components, and this unbalanced quantity can be represented with a symmetrical components. So sequence network we need to study in this. So the methods of getting this sequence components, we are having how we can get this sequence component. So VA1, VB1 and VC1. So these are your positive sequence component, sequence vector, and the second is the negative sequence vector. We are having VA2, VB2, VC2, and it is a negative sequence vector. And zero sequence vector VA1, VA0, VB0, VC0 are the zero sequence vector, and it is having equal magnitude. There is no phase displacement. So now we can represent any of this quantity in terms of one particular, say B phase and C phase in terms of A phase, so that the time taking to analyze the system it gets reduced. So you can see that in order to represent this VB phase or C phase in terms of A, we required operator A. This operator A means it is having a magnitude of 1 at an angle of 120 degrees in anti-clockwise it can rotate. So we can see that VA1, now we are having 120 degree displacement, and so this C phase C1 is nothing but A at an angle VA1. So after another 120 degrees, so it is A square, one angle 120 degrees, one at an angle 120 degrees. So it is A square times VA1. So VB1 can be represented as A square times VA1, VC1 can be represented as A times of VA1. And this that is we are writing here. So VA equal to nothing but this VA0, VA1, VA2. So this, so first next one is about our negative sequence vector. So negative sequence VA2 is nothing but VA2, and this VB2 can be represented. It is a VB2, and this one is VC2. So we can see that this one is nothing but VB2 is nothing but A times of VA1, so it is A square. Okay. So with respect to VA1, if you take it, it becomes A times of VA1. A times of VA1, it is VC2 means this one. So it is A times of VA1. So VA equal to nothing but the A phase is nothing but VA0 plus VA1 plus VA2. It is a phase. B phase is nothing but VB0, VB1, VB2. And C phase is nothing but this V phase we can represent it as this VB0, we can write as this is the VB0. So VB0, VA0 all are in same phase sequence. So it is VB0, we can write as VA0, and VB1. So this is the VB1. So VB1 is nothing but A square times of VA1. A square times of VA1. So it is a square times of VA1. VB2 is nothing but it is a 120 degrees displacement. So it is A times of VA1. And here it is A square times of VA1. Then it is, so VB1 is nothing but A square times of VA1, and VB2 means this one. It is A times of VA1. A times of VA1. It is VA2 now. So it is A times of VA2. So A times of VA2 we can write it. And next one is zero sequence for the C phase, VC equal to nothing but VC0 plus VC1 plus VC2, this one. So these three quantities can be added. So VC1, this one is same. So this VC is nothing but VA0 plus, so it is same phase sequence, and VC1 means this one, A times of VA1. So it is A times of VA1. VC2 means this is A square. It is 120, 120. So it is A square times of VA2. So A square times of VA2.
Methods of getting sequence component. First is VA equal to VA0 plus VA1 plus VA2. So we have the positive sequence, negative and zero sequence component in a balanced quantities. This unbalanced quantities VA, VB, VC are represented with positive, negative, zero sequence components. And VB equal to VA0 plus A square times VA1 plus A times of VA2. and VC is nothing but VNR plus A times of VA1 plus A square times of VA2, and this we can write these particular relations, we can write as from these equations VA, VB, VC. So these are the unbalanced quantities that we are writing as 1 1 1 in a matrix forms. This 1 1 1 1 A square A 1 A square, and VA not VA1 VA2 are the these are the symmetrical components. So we are representing this unbalanced quantity into a balanced symmetrical components. Then this one is this one we can write as a matrix A that represent A is nothing but 1 1 1 1 A square A 1 A square, and A is nothing but 1 at an angle 120 degrees, A square is nothing but 1 at an angle 240 degrees. Then we can see this these are the phasor quantity VA, VB, VC are the phasor, and it is an unbalanced quantity. VA0, VA1, VA2 are the sequence components, so we are giving a notation as VS. So VP equal to A into VS. And again, if you can, if you the unknown quantities are the symmetrical components, then we can write as VA0, VA1, VA2 equal to A inverse of VA, VB, VC, and VS equal to A inverse of VP. And you can see that A inverse means we can calculate this A inverse is adjoint of A divided by determinant of A. Then you can calculate this A inverse, that is say 1 by 3, 1 1 1, 1 A square, 1 A square A, and VA, VP, VC. Then you can calculate this A in terms of A square. And power in terms of symmetrical component, we can calculate the power in three-phase system can be expressed in terms of symmetrical component of associated voltage and currents. The power flow into a three-phase system through these lines ABC, and that power calculations we have the relation is S equal to P plus JQ. So normally in case of balanced, we can calculate S is nothing but VI conjugate. Okay, that is we are representing 3V phase I phase cos phi. 3V phase I phase cos phi. So we need to calculate this power in case of a symmetrical component. S equal to P plus JQ, that is VA IA conjugate, and VB IB conjugate, and VC IC conjugate. Now we can write this power equation. So where VA VBC are the voltage to the neutral at the terminals, and IA IB IC are the current flow into this system in three phase lines. So if you write in matrix form, S equal to VA VB VC and IA IB IC. And this VA VB VC we can write as VA VB VC whole transpose IA IB whole conjugate. So it is S equal to nothing but we know that VI conjugate. So it is the conjugate. So VA VB VC we can write as in three phases VA VB VCs and the corresponding current IA IB IC. Now we can write this VA VB VC. This one we can write as, so we know that VA VB VC is nothing but A means it is 1 1 1 1 A square A 1 A square into this VT means VA0, VA1 and VA2 this one. So it is VA VB VC that we are calculated in this equation. So this is the equation we are getting as VA VB VC. This is the unknown unbalanced quantities, and we are presenting in symmetrical quantity that we are getting this in this relation. Then we can say VA VB VC and 1 1 1 1 A square A. Now we can this quantity is nothing but this VP equal to, we are saying that it is A times of VS. From this relation, if you write this VA VB VC, we can write as S equal to, here S equal to nothing but this in place of this VA VB VC whole transpose, we can write as A into VS whole transpose into this IA IB IC. This current also we can write this is the voltage relation, and you can write same in a current relation also. So the current relation is IA IB and IC equal to 1 1 same, and it is IA0, IA1 and IA2. Now you can write this one also, this IA IB IC whole conjugate. This IA IB IC you can write as IP equal to nothing but A times of this IS. A times of IS whole conjugate. right? So we can write here A times A into Vs whole transpose A into Is whole conjugate. Now using this reversal rule of this matrix, so we know that AB whole transpose is nothing but B transpose into A transpose. In matrix mathematics we learn that AB whole transpose is equal to B transpose into A transpose. Now we can write that relation here, Vs transpose into A transpose. Here AB whole conjugate means A conjugate and B conjugate. So you know that AB whole conjugate is nothing but it is A conjugate into B conjugate. So it is A conjugate into Is conjugate. So Vs Is means it is in terms of sequence components. So then we can write further, this one is, we know that A transpose is nothing but A. A transpose equal to A. If you calculate this relation, and A and A square are conjugates. So if you write this 1 1 1 1 1 1 1 A square A 1 A square. So this one if you write the transpose, so row columns if you change, so you can get same value. So means A transpose equal to A. And now we can substitute here. So in this place of this Vs transpose, Vs means this one. So this Vs means Va0 Va1 like that. So we can calculate here Va0 Va1 Va2 and it is Vs transpose into A. So here we are getting as Vs transpose into A transpose or A, it is same, into A in Is conjugate. Now we can see that, so Vs means Va0 Va1 Va2 and A transpose means 1 1 1 1 A square A 1 A square. Here it is A square and A both are. So you can see the A transpose, it is 1 1 1 1 A square 1 A square A. So you can get here it is 1 1 1 1 A square A 1 A square. So it is your A value, and A transpose means it is 1 1 1 same value of A transpose you can get it. Here we can see that it is 1 1 1 1 A square and it is conjugate. A conjugate means 1 1 1 1 A square A. So we can get A value is, A value we know that 1 1 1 1 A square A 1 A square. If you put a conjugate, it will be 1 1 1 1 A square conjugate, it is A and it is A square 1 A square A. So it is a conjugate. So A you know that it is minus 0.5 plus J 0.8. If you put a conjugate of this one, it is minus 0.5 minus J 0.866. So this value is nothing but A square. So A conjugate is nothing but it is A square. So if you substitute like that, it is A conjugate and it is A transpose and it is A conjugate into I conjugate. I conjugate means it is Ia0, Ia1, Ia2 whole conjugate. Now we can multiply these two. So you can see these two equations if you multiply, so you can get this relation as, so Va0, Va1, Va2 into 1 into 1, 1 and this 1 plus 1. 1 into 1, 1 into 1, 1 into 1, right? And 1 into 1, 1 plus 1 into A plus 1 into A square. And 1 into 1, 1 plus, so multiply these two matrix, this A transpose and A conjugate, we are multiplying now and we are getting as 1 plus A square plus A. And if you multiply this one, it is 1 into 1, 1 plus 1 A into A square plus A. Here it is 1 into 1, 1 plus A square into A cube plus A into A square, it is again A cube. And 1 into 1, 1 plus 1 into A square into A square, A power 4 plus A cube. 1 into 1, 1 plus A square. 1 plus A into A square plus A cube, A power 4, right? And you can see that here 1 into 1, 1 plus A into A cube plus A square into A cube. Now we are multiplying these two matrix and it is Ia0, Ia1, IA2 whole conjugate. Now you can see the 1 plus 1 plus 1. It is now we can see equate this VA0, VA1, VA2 into it is 3. 1 plus A plus, you know that 1 plus A plus A square is nothing but 0. This is 0. This one also 0. 1 plus A square, it is 0. 1 plus A cube, A cube is nothing but 1. Then it is 1 plus 1 plus 1, it is again 3. 1 plus A power 4 into, so A cube is nothing but 1. So A power 4 is we can write as A cube into A. Then it is A cube means 1. 1 into A, it is A. Then you can get as this 1 plus A plus A cube means again this second relation we are getting as 1 plus A power 4 plus A square. Sorry, it is A square. Then it is 1 plus A square. So we can get as 0. And this one is 1 plus A square again 0. And 1 plus A square plus A power 4. A power 4 means 1 plus A square plus A. It is also 0. And 1 plus A cube means 1. Then it is 3. So finally we can get as IA0, IA1, IA2 whole conjugate. Then VA0, VA1, VA2 into 3 0 0 0 3 0 0 0 3. So and IA0, IA1, IA2 whole conjugate. So if you multiply this one VA0 into 3, so you can get as VA0, VA1 into this one is 0 and again VA1, VA2. So it is we can get as 3 VA0, 3 VA2, 3 VA2 and IA0, IA1, IA2 whole conjugate. Now you can multiply this, then finally we can get as 3 times of VA0 into IA0 conjugate plus 3 times of VA1, IA1 conjugate plus 3 times of VA2 into IA2 conjugate. So it is a power relation in case of 3-phase in terms of symmetrical component. So it is the relation we are getting here 3 into it. This we can write as 3 into unitary matrix. It is 1 0 0 0 0 1 0 0 1. So it is a unitary matrix. So if you multiply this, we got this is the power in case of a symmetrical component in a 3-phase system. So that is the power relation we can get set A transpose again 3 into U. Then we can get thus the complex power in this 3-phase is S equal to VA IA conjugate. This is in unbalanced quantity. Then in case of symmetrical component it is 3 IA VA0 IA0 conjugate, 3 times of VA1 IA1 conjugate plus 3 times of VA2 IA2 conjugate. So complex power can be computed from this symmetrical component of this voltage and current of unbalanced 3-phase circuits.
So in case of power in terms of symmetrical component, the power in 3-phase system can be expressed in terms of symmetrical component associated with the voltage and current. And the power flows in the 3-phase system through the line, through 3 phases, A, B, C phases. That we can write as S equal to nothing but P plus JQ. We know the power relation S equal to P plus JQ. That we are writing as S equal to nothing but VI conjugate. So S equal to VI conjugate. With respect to A phase, it is VA into IA conjugate, and with respect to B phase, VB into IB conjugate. C phase, it is VC into IC conjugate. VC into IC conjugate. So like that, we can calculate the power. So where this VA, VB, VC are the voltage to the neutral terminal, IA, IB, IC are the current flow into the system in the 3 lines, and the matrix forms if you write S equal nothing but VA, VB, VC and IA, IB, IC. So this is the voltage. If you multiply these two, VA into IA whole conjugate. So VA into IA conjugate, VB into IB conjugate, VC into IC conjugate. Further, if you write this one is in transpose, VA, VB, VC whole transpose, IA, IB, IC whole conjugate. And this S equal nothing but we are writing as this VA, VB, VC whole transpose, we are writing A into V whole transpose, and this IA we can write as A into IA whole conjugate. And using this reversal rule of this matrix algebra, we can know that AB whole transpose is nothing but this B transpose into A transpose. So like that, if you write here the V transpose into A transpose into A conjugate into I conjugate, and A transpose is equal to nothing by is equal to A. It is asymmetrical. So A transpose equal to A. If it is a symmetry, then A and A squares are conjugates. So now we can write this relation as VA naught, this A, B, C in terms of this VA naught, VB naught, VC naught. So this VA naught, VA1, VA2 is equal to nothing but this voltage V nothing VA, VB, VC, VA, VB, VC. We are writing as VA naught, VB naught, VA naught, VA1, VA2, 1, 1, 1, 1 A square A, 1 A, 1, 1, 1, 1 A square. It is your, this one is A transpose means A means 1 A square. Okay. So 1 A square is, it is A and it is your A transpose. Okay. And then we are calculating A transpose and A conjugate are equal to 3 into E. If you multiply this 2, then we can get A into A transpose into A, we can get 3 into U. 3 into U means 3 into unitary matrix 1 0 0 1 0 0 0 1. So this unitary matrix we can get by a 3 by 3 matrix. Now we are getting as this VA naught, VA1, VA2. This one is a unitary matrix into IA naught, IA1, IA2 whole conjugate. So thus this complex three-phase power is given by, so S equal nothing but VA into IA conjugate, VB into IB conjugate and VC into IC conjugate is equal to nothing but 3 times of, so this multiplication we are getting as 3 into U. So it is 3 into unitary matrix we can get it. Then it is VA naught, VA1, VA2, VA naught, VA1, VA2. So then we are getting as 3 into VA naught into IA naught, 3 into VA1 into IA1 plus 3 into VA2 into IA2. It is a total power we are getting in case of 3-phase. So single, in case of 3-phase we are getting that S equal to VA into IA conjugate, that VA into IA conjugate we are getting as these relations. So we are getting this relation of 3-phase power. This complex power can be computed from the symmetrical component of voltage current of an unbalanced 3-phase circuit. So these are the how this 3-phase complex power can be calculated from a symmetrical component is 3 times of VA naught IA naught plus 3 times of VA1 IA1 plus 3 times of VA2 IA2, not like VA into IA, VA naught IA naught like. So it is 3 times of VA naught, 3 times of VA1 IA1, 3 times of VA2 IA2. So this next we can see that sequence impedances in unsymmetrical fault calculation, each piece of equipment will have 3 values of impedance, once corresponding to each sequence current. It is having a positive sequence impedance Z1, negative sequence impedance Z2 and 0 sequence impedance it is Z0. So this sequence impedance offered by an equipment or a circuit to the positive sequence current is called positive sequence impedance and it is represented by Z1. And similarly, the impedance offered by any circuit or equipment to a negative or 0 sequence current are respectively called a negative sequence impedance Z2 and the 0 sequence impedance is Z0. And the sequence network in 3-phase balanced systems, each piece of equipment or a circuit offered by only one impedance, that one offered positive or normal sequence current, and this is expected because of absence of negative and 0 sequence current in the 3-phase balanced system. So in balanced system, we have only positive sequence component. In case of 3-phase unbalanced systems, each piece of equipment or circuit will have 3 value of impedances. Here only one impedance we are having if the 3-phase balanced system is balanced system, 3-phase balanced system. But in case of unbalanced system, we have 3 value of impedance, that is positive sequence, negative sequence and 0 sequence impedances. So the positive negative sequence impedance of a linear, symmetrical and static circuit like transmission lines, cable or transformer, static loads, these positive negative impedances are equal and are the same, those used in analysis of balance conditions. And this is due to the fact that impedance of circuit is independent of phase order provided applied voltage are balanced. So you can see that transmission lines or in cables or transformer or static loads, we have the positive and negative sequence impedances are same. The zero sequence impedance depend upon the path taken by zero sequence current. So the zero sequence impedance is will be depends on the path of a zero sequence current. And as this path is generally differ from this path taken by the positive and negative sequence currents, so and therefore zero sequence impedances is usually different from the positive or negative sequence impedances. So what are the sequence impedance of a synchronous generator? So the sequence impedance of a synchronous generator, we can see that unloaded synchronous generator or motor grounded through this reactance grounding. So this is generator, we are having EA, EB, it is induced EMF and it is having grounded with the Zn. Neutral is grounded with this Zn. So this positive sequence network, since the asynchronous machine is designed with a symmetrical winding, it is induced EMF of positive sequence only. And no negative or zero sequence voltage are induced in it. When the machine is carries positive sequence current, only this mode of operation is the balanced mode. So if it is carrying only positive sequence current, then it is in under balanced condition. And the generator voltage are a positive sequence only. And since the generator is designed to supply balanced three-phase voltages, so therefore the positive sequence network is composed an EMF in series with the positive sequence impedance. So this particular synchronous machine means a motor or generator can be represented by a voltage source in series with the impedance. In series with the impedance, this impedance is a positive sequence impedance, and it is the EMF induced in there. So the generator voltage are of positive sequence only, and the generator is designed to supply balanced three-phase voltage. So the positive sequence network is composed as an EMF in series with the positive sequence impedance. And EA, VB, EC are the induced EMF of this three-phase when a fault takes place at the machine terminal. Currents IA will be flows to the neutral through the via this Zn. And unbalanced line current can be resolved into the three symmetrical component IA1, IA2, IA0. So the negative zero sequence network contain no EMF. So negative sequence and zero sequence does not having any EMF induced in that, but induce the impedance of the generator to the negative and zero sequence current respectively. So in case of negative and zero sequence, we need to represent only this reactance only. This it is a generator, it is having a negative sequence impedance and it is a zero sequence impedance. But in case of positive sequence, we need to represent a voltage source in series with the reactance. Here only one reactance. In zero sequence also only reactance. The armature reaction, if field caused by the positive sequence current rotate at synchronous speed in the same direction at the rotor, so it is stationary with respect to the field excitation. The machine equivalently offered the direct axis reactance whose value reduced from the subtransient reactance to the transient reactance and finally to the steady state reactance is XD as a short circuit transient progress in the line. So if your induction this synchronous machine is there, and this synchronous machine, if it is having a fault at this terminal, if the fault is there, so this fault, during the fault, at immediate after the fault, we are having a transient condition. After that subtransient, then it is having steady state. So we are having during the transient, we are having the impedance is XT double dash, and during the subtransient, at the transient subtransient to the transient, it is XT dash. It is during transient and it is subtransient, and XD during steady state. So this is the reactance offered by the synchronous generator if the fault is at the terminal of the synchronous machine. If the armature resistance is assumed negligible, the positive sequence impedance of the machine is x1 equal to j times of xg double dash, xt dash and xt. So if one cycle of transient of interest, that is a subtransient period, and during transient it is 3 to 4 cycles, the xt dash, and then it is having a steady state value is the xt. So the positive sequence voltage of terminal with respect to reference bus is given by the voltage of this particular synchronous machine can be represented as voltage source in series with the reactance, then it is connected to like this. It is a reference. So all phases, it is a positive sequence network for A phase, B phase, C phase, it is same. Next, negative sequence network. A synchronous machine does not generate any negative sequence voltage. So synchronous machine during the negative sequence component, it does not generate any voltage. The flow of negative sequence current in the stator winding is create an MMF which rotate at synchronous speed in a direction opposite to the direction of the rotor. So it will be rotate opposite to the rotor direction, and twice the synchronous speed with respect to stator, 2 times of ns. The negative sequence voltage of terminal with respect to the reference is given by VA2 is nothing but minus Z2 into IA2. Only the negative sequence impedance will be there, that we can see at the terminal it is minus Z2 into IA2. So it is a voltage we can represent. So that is, we can see that it is having Z2 for A phase, B phase like this, and if you write the one particular phase, it is IA2, then corresponding voltages, if you take VA2 is nothing but, this VA2 is nothing but minus IA2 into Z2. So next one is, we are having another network we need to represent is zero sequence network for a synchronous machine. So no zero sequence voltage is induced during the sequence, no zero sequence voltage. Zero sequence voltage also zero in a synchronous machine. The flow of zero sequence current in the stator winding produce 3 mmf which is in phase. And if each phase winding produces a sinusoidal space mmf, then the with the rotor removed, the flux at the point on the axis of the stator due to the zero sequence current would be zero at every instant. The zero sequence current flow through the neutral impedance, that is Zn, and the current flow through this impedance is 3 times of Ia0. So we can see that the this synchronous machine, if it is grounded like this, then it is having a reactance. Then it is 3 times of Ia0 of current will flow through this neutral if there is a fault is occurred like this. So it is a fault. So current will flow from this to neutral, it will flow like this. So this zero sequence voltage drop from the point to the ground, it is minus 3 Ia0 into Zn and minus Ia0 into Z0. So it is Z0 is nothing but Zn plus 3 times of Zn plus Zg0. Okay, so it is a zero sequence current, and 3 times of Zn is the impedance offered by this grounded. Thus Z0 is called nothing but 3 times of Zn plus Zg0. The zero sequence voltage of this terminal with respect to the reference bus. So if you take, this is the voltage, if you take this loop, then we can get as VA0. This is the VA0. If you take this voltage with respect to, then it is minus Ia0 into Z0. So it is a current, neutral current will flow like this, this zero sequence current. Then it is minus Ia0 into Z0. Z0 means it is Z0 plus 3 times of Zn. Zg0 plus 3 times of Zn. So you can see that the zero sequence current Ia0, Ib0, Ic0 will flow through this neutral current. So it is having Ia0. So you can see the Zg0 plus 3 times of Zn. It is your Z0. So this sequence network of this, we can represent positive sequence network having a voltage source EA in series with the impedance. Then we can get a VA1. So this is a VA1. If you take the loop analysis of this one, then you can get minus EA plus IA1 into Z1 plus VA1 equal to 0. From this, VA1 is nothing but EA minus IA into Z1. Next, you can see that here it is having the VA2 negative sequence impedance. Then it is minus. It is the current will flow like this, plus minus. Then it is if you take the loop analysis, this one, it is plus IA2 into Z2 plus VA2 equal to 0. From this, VA2 is nothing but minus IA2 into Z2. That is a negative sequence voltage induced in this. Similarly, if you take the loop analysis, this one, it is Ia0 into 3 times of Zn plus Ia0 into Zg0 plus Va0 equal to 0. From this, Va0 is nothing but minus of Ia0 into Zg0 plus 3 times of Zn. So it is a reference bus, zero sequence network, and it is a negative sequence network, and it is a positive sequence. So positive sequence network can be represented with a voltage source in series with the reactance, and this negative sequence is represented only the negative sequence. Reactance is represented as Z2, like this, only reactance. Here it is Zg0 plus 3 times of Zn. So this is the positive sequence, negative sequence, zero sequence network of a synchronous machine. Next is sequence diagram for transformer. Now we can see the sequence network for a transformer, transmission lines. So positive sequence, negative sequence will be same, but zero sequence will be different. So the positive negative sequence diagram for a transformer is similar to that of transmission line. So means it is simple transmission transformer or transmission line. We can represent it as, say, positive sequence, it is Z01 or Z02, like this. Only we can represent like this. But zero sequence network will be different. The zero sequence network depend upon both how the transformer is grounded and its type of connection. So transformer we are representing like this, and this transformer, how this primary and secondary is connected. So how this primary and secondary is connected, based on the zero sequence will be depend. What I already told, that if there is a fault is occurred at this terminal and it is a grounded fault, if the grounded fault is there, then only the zero sequence will be exist. And this transformer is not having any ground connection, there is no current flow takes place. Okay, but if it is having a ground connection is there, then there is a ground, this particular current can be flow. So based on this connection of this transformer, we can see that how this zero sequence network can be connected, we can do it. So if a transformer is connected with a star grounded and star grounded, then we can see that, so we have the connection like series and shunt elements. So series shunt switches are connected for delta and star winding of transformer, represented as follows. So it is the representation of transformer. It is having, these are the reactances, these are the switches. So these are the shunt switches, these are the series switches. Series switches and shunt switches will be there, and connection of, consider the delta star transformer connection with a star grounded as follows. So if it is a star grounded is like this, then how we can represent is the following. So primary is a delta connection, so the shunt switch of the primary side is closed. Shunt side, delta connection means, delta means we need to close the, delta means shunt switch will be closed, switch is closed. And this star grounded means the series switch will be closed, series switch is closed. Only star is there like this, then series switch is open. So this, based on this series and parallel connections, so we can see that example is that delta star having grounded. So primary side delta is there, delta means shunt switch is closed, this shunt switch is closed, so that shunt switch is closed and it is Z0, and star grounded, so Y grounded, this one is closed, this is the closed. So it is the primary and secondary side, like this it is the connection. The primary is delta connected, shunt switch of primary side is closed and series switch is left open. Secondary side is star grounded, therefore series switch is closed and the shunt switch is left open, this switch is open. It is the zero sequence network for a transformer. Similarly, you can see the delta means this shunt switches are closed, so this will be open. Next, star grounded, like this, star grounded means this switches will be closed. And here you can see that Y means it is a open circuit, and then it is a Z0, then it is having connection like this, it is for star Y grounded. And delta means shunt switch will be closed, and it is star means this one is closed. Delta means this switch is closed and it is a open. So it is a zero sequence network of transformer. So similarly for different connections, say star, here it is grounded, so it is connected here, and it is a open switch, and both are closed. And star means this one is closed. Here it is delta is closed. Both delta star means star it is opened. Delta means this switch is closed, and it is open. And delta means both are closed. So this is the way of connection of this zero sequence transformer. And sequence network of transmission lines. So transmission line, so transformer I told the positive sequence and it is a negative sequence. Zero sequence based on the connections. Positive sequence Z1, Z2, it will be same. Only reactance will be there. So in case of transmission lines, we can see the reference bus and it is Z1 and it is a positive sequence network. It is also similar. It is a negative sequence network and it is a zero sequence network. So in case of transmission line, just we represent like this. All are same. Positive sequence, negative sequence, zero sequence will be same. Sequence network for load. Based on the load, we can see that the load connections we can connect like this for a positive sequence and negative sequence and zero sequence. The load also same, only shunt wise we need to connect it. Thank you. So today we seen about the sequence networks for a synchronous generator, transmission lines and transformers. So synchronous generator, we are having the positive sequence, negative sequence, zero sequence networks. So in case of positive sequence in a synchronous generator, it is having voltage source in series with the reactance. For a negative sequence, it is only having one reactance, and zero sequence, it is also only one reactance. In case of transmission line, the positive sequence, negative and zero sequence, it is only single reactance. In case of transformer, the positive and negative sequence, it is having only one reactance, but in case of zero sequence, it is having based on the connection, primary and secondary connections, we need to connect the shunt or series switches based on the way of primary and secondary is connected. Then we can frame the zero sequence network. And if you are having the next to, we are going about on the fault analysis. Based on this sequence network, we need to connect all this network based on your single line diagram, and we need to calculate the fault analysis. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.